Okay, number 5. Consider the 100 megabit per second fast Ethernet network depicted below. For each user, the last byte of the corresponding IP address and MAC address is listed. First up, what is the effective data rate observed by midden 01? Show work. Okay, so we're looking at midden 01. Middens are all these computers, and midshipman computers are here. 01 is this computer, so it is connected to a bridge and 1, 2, 3, 4, 5 other users. So we have 100 megabits per second, Mbps, divided by 5 users plus the bridge equals 16.67 megabits per second. Okay, so we're just counting the number of users connected to the bridge, and we do include the bridge in the calculation. The rest of them don't matter because the bridge is arbitrating between the rest of these connections for you. What is the effective data rate observed by instructor? So the instructor is connected by a hub, which doesn't matter, to a bridge. So there are effectively 2 users on this network, the instructor and the bridge. So we have 100 Mbps divided by instructor plus the bridge equals 50 megabits per second. Next up, if midden 05 and midden 11 were to switch places on the network, would any changes be required to their Ethernet addresses? Their Ethernet addresses are their MAC addresses. As we know, MAC addresses do not change or shouldn't change unless they're being spoofed. So there would be no changes. This would be false. We would not require changes to their Ethernet addresses to connect to the network. They would change their IP addresses most likely, but they wouldn't have to change their MAC addresses. Next up, a 4,525 byte packet were to be transmitted. How many frames would be required? Show work. So if we look here at the frame diagram, we can see that data and padding, the network layer packet in a frame, can be from anywhere from 46 to 1500 bytes. So I'm just going to write these here. Min equals 46 bytes. Max equals 1500 bytes. Okay, so if we have a 4,525 byte packet, the maximum we can fit is 1500 bytes per packet. And that's going to give us something like 3 remainder 25, because we have 1500 times 3 is 4500. We have 25 left over. So because it's 3 remainder 25, we need 4 frames. We can't fit 3 plus 25 into 3, so we need a 4th. So then, if necessary, how many bytes of padding are required in the last frame to transmit the same packet from part D? If none, what is the total size of the last frame? Show work. So in this case, we know that we're going to require 4 frames. We have 3 that are completely full with 1500. So the last one is what we're going to use the remainder here to figure out how much data we need to pad out in that last frame in order to send that 25 bytes in a frame. So the minimum is 46 bytes. So we have 46 bytes minimum minus the amount of actual data that we want to send, 25 bytes, is going to give us 21 bytes of padding. Okay, next up. An Ethernet frame sent by midshipman 01, hardware address 0001 020304AA, containing an IP packet length of 0800 is shown below as it appears in Wireshark. The data and padding portion of the frame is bolded for your convenience. There are 4 rows of hexadecimal data read from left to right and top to bottom. Answer the following questions based on this frame. What is the address of the intended recipient of the frame? So in this case, we're trying to lead you to it a little bit. We can look back at the definition of the frame and see that what we have here in this frame is destination address for 6 bytes. So 6 bytes of destination address. And I can sort of box those. 6 bytes of source address. That source address should match 0001 02 03 04 AA because they told us it was sent by midshipman 1 with that hardware address. And then we have the length or type, which they told us is 0800 for being an IP packet. So the address of the intended target is the destination MAC address. That's 01:02:03:04:05FF. And I'm just taking that from the bytes here in the destination address part of the frame and writing it as a MAC address. What is the length of the packet header in bytes? So now we need to look at the IP packet format. That is at the bottom here. So we have the IP header format. So the first thing in our packet is the IP header. That's coming right after the frame, right? So we have destination, source, length, and then the data and padding, which is the network layer packet. So that's what we're looking at here. So 4 bits is a single hexadecimal character, or a single hexadecimal digit. So 4 represents 0100. That's 4 bits. 5 is going to represent 0101. And so if we look at the packet here, version is 4 bits, hlen is 4 bits, and we're looking for the length of the packet header in bytes. So the packet header is going to be 5, and if we remember from hlen, it's times 4 bytes because it is compressed. So that's 20 bytes total. Okay, and then finally, we have what is the total length of the packet in decimal. So the total length is going to come after version and hlen, and then we're going to have 8 bits for service. So 8 bits is 2 decimal characters, so that's service. And then the next thing after that is 16 bits for total length. So the 16 bits there are 0x0028. We need to convert 28 into decimal instead of in hexadecimal. And so we need to calculate 2 times 16 plus 8 is equal to 40 bytes total length. Okay, so that is it for question number 5.